but you get also the information about the change of the population. And here are separate maps. The upper one just showing the population that is lost in certain areas. So now the areas pop out where the population shrinks. Here, these are two cities in the former eastern part, the GDR, German Democratic Republic. These are areas around cities. You see them here as well. So this area around the city and this area around another city, they are more pronounced in this map. And the same is true here for this area. There is a former mining industry, so there are structural problems a bit similar to the Dongbei region in China, where there were a lot of coal industry and so on. And because of the situation in the world market, these areas, they have all problems now, economic problems, and this downturn leads to loss of population. And here in the lower map, you see the areas where population is rising, extremely rising within Germany. So this is Berlin as well as around Berlin, and Munich, also Frankfurt, or here this is Dresden and Leipzig, two other cities in East Germany. So they pop out even more here in these maps because there is no other information included, just these parts. And the background map here is unchanged. So therefore, there is no distortion of the shape of Germany here. The background map here, the situation is a bit different. So there is slightly distorted, but the distortion mainly occur within, because it's about all the parts within Germany. So it's not so much about the population all over Germany. Therefore, the distortion is also within the country. And that one, it's also about population of Iceland. Well, I don't like that map, I have to say. It just looks strange, and for me this is not so good example. You see in the back the original shape of the island. It's northwest of Europe. It's between Europe and Greenland, and population is less than 400,000 people all over the island. But here the distortion is so strong, the shape is totally lost, and only if you're really familiar with the area you have a chance to interpret that map. So for other people it's quite curious. A good idea is to write down the names of cities here, the capital Reykjavik here, for example, or Akureyri, which is the largest city in the northern part, and so on. So then it's easier to identify which of the parts of this cartogram belongs to which area of the country. But it's still, a bit strange. So I think that's a bit too much of distortion here. This is another interesting example of the US. So you have the US states, and it's about population. I couldn't find a year, but just as an example, how such maps can be, or how this technique can be applied in different ways. So here you see that the states are located as much as possible in the center of the original shape of those states. You see that only few people live here in the Midwest, and it's quite different to these states here. They're always important when there are US elections, also California, Florida, Texas. So these are the most interesting countries because Yeah, there are more people who vote, and therefore there are more of these who vote. They have a special name, but I'm not so familiar with their system. But of course, you see the big difference here between the different parts of the US. And it's an example of a non-contiguous cartogram. So the shape of each state is perfectly preserved, but they are not connected to each other, which is not so big problem here, but it becomes a bigger problem here, where some states, for example, here, New Jersey, is quite far away from its original position. It would be here, because this is not possible here. And the last example is not a cartogram. So this is no cartogram. This is just a kind of diagram. So these diagrams together represent the whole world. And this diagram impression here is more important or prevails over a map impression, because these countries are not located here in any spatial relation to each other. So here you have the United States, here you have Italy, here you have the Russian Federation, and so on. The topic here is emissions. So you can compare here more than 250 years of emissions in the larger one, and then just 1 year in the smaller one. And there's a distinction here in the colors, the G20 countries and those countries that do not belong to the G20. So this is the brighter color in this area here. So most of the countries are G20 members, but the whole diagram is hard to interpret. It's a bit misleading, because it's hard to grasp the difference here between 1 year and 250 years. Of course, now it's larger, but how to compare that? So the whole diagram is not really a good solution. Then I want to come to another topic, is arithmetic mapping. Algorithmic maps depict smooth, continuous phenomena such as rainfall, barometric pressure, and the Earth's topography. So that's important. It's about continuous phenomena, not abrupt, changing, or discrete phenomena. Data for algorithmic mapping are sampled from an underlying phenomenon at point locations termed control points. Two forms of data can be collected at control points. True point data, this is measured at a point location, for example, snowfall at a weather station, and the maps produced are called isometric maps. And conceptual point data, collected over an area or volume, but are presumed to occur at point locations. For example, population for counties, and the maps produced are called isopleth maps. Isopleth maps. So there are two different names here, isometric maps and isopleth maps. Be cautious when working with conceptual point data, as the assumption of continuity might not be met. For example, population-related data might be characterized by sharp discontinuities that would be more appropriately mapped by the dot or decimetric method. So there are other methods that might be more appropriate. So be critical with this method, especially when it's about conceptual point data. So as you have just heard, these conceptual points are related to areas, but they're treated like points, and these points should represent the area. And for some kind of data, it depends on the topic. For some kind of data, this works well, but for others not. So check the continuity. So do the values from one area to the next, or one conceptual point to the next, do they change abruptly or more continuously? So if they change more continuously, the method will work. If they change abruptly, the method will not work well. As with the choropleth map, the isopleth map requires standardization of the data to account for the area over which conceptual point data are corrected. For example, it would make no sense to map the raw number of people in counties because a larger county would tend to have a higher population total. So therefore, you need standardization. We talked about that. Available methods of standardization for isopleth maps are identical to those discussed for choropleth maps. So you'll find this section there. A key problem in isarithmic mapping is that data are available only at irregularly spaced control points, whereas the phenomenon is presumed to exist throughout the region of interest. So you have only a certain number of control points, but you know, of course, that the phenomenon is all over the area, like precipitation or temperature. So you measure only certain control points. Therefore, interpolation is necessary to determine the values of intermediate points. The four main interpolation methods are as follows: manual interpolation, automated interpolation by Delaunay triangulation, automated inverse distance interpolation, also called gridding, and automated interpolation by kriging. So that's the difference, gridding and kriging. First, manual interpolation. Manual interpolation, or interpolation by eye, was the only approach available prior to the development of computer-based methods, which did not become popular until the 1970s. It is important to know about manual interpolation to understand the basic idea of interpolation. Therefore, it's good to start with this method to get the basic idea of interpolation. It is also frequently used to assess automated methods. So we have to check automated methods if they really work well. And in some situations, it might still be helpful to do some manual interpolation. Manual interpolation is accomplished by mentally connecting neighboring control points with straight lines and then linearly interpolating along these lines to create contours or isolines of equal value. Linear interpolation refers to the idea that the contour line is positioned proportionally between the control points. I will show you an example on the next slide. The strict definition of linear interpolation produces an angular contour line. As such angularity cannot be found in natural phenomena, contour lines are smoothed, for example by splining, which involves fitting a mathematical function to points defining a contour line. I will also show you an example for that. Manual interpolation might not always find an appropriate value between existing control points. For example, when control points are positioned near the corners of a square, it might not be clear where to draw the contours. It's, of course, hard to understand, and you just hear or read it, but with the example that I will show you, it's easy. So here you see the example of the basic idea of manual interpolation. So you have control points, these black dots here, and then you want to interpolate certain values. So at these control points, there are the measurements. So you have values 34, 31, 36, 26. And now, for example, you want to interpolate a contour line with the value 30. So here you see it's between 26 and 34. So you draw a line, and then you split the line where 30 would be. Here it's just in the middle. Here it's not in the middle, of course, between 26 and 31. But then you just it's easy to find the right relation here. It's just an example to show you the basic idea. So you have then three locations here, 3 points that you can connect, and so you get the contour line with the value of 30. Now, one problem is that with this method, you get this angular contour line, and then you need to smooth it. So you can fit a smooth curve, a spline, to such an angular line. Then to smooth it out, you get this broader, darker line for here it's for the value 40. So you have these control points here, and then this line is interpolated. And the problem with the 4 points in a square, if you manually try to find the right position of the contour lines, you have to check out the situation. Here you have 27, 17, 32, and 14. These are the values at the control points. And if you use this method that I've just explained to you, you can draw 2 contour lines here for the value of 25, here and here. But as you see here, with the same values, you can also draw these lines here. So you have here 25, here 25, here 25, here 25, and you can connect these points along the line here with these curves or with these curves. So what is the right result? If you do it that way here, that means this area is below 25, because here you have 14, here you have 17. If you do it that way, this area is above 25, because here you have 27, here 32. So the solution is to interpolate the point here by averaging the 4 original control points. So if you average these 4 points, you get 22.5, and this is below 25. So the right solution should be more similar to that one. As you see, the lines are drawn in a bit different way compared to here, but still this middle section is below 25. So this is how to solve this problem. The second method is automated interpolation by Delaunay triangulation. A key step in any triangulation is connecting neighboring points to form a set of triangles. Delaunay triangles, named after Boris Delaunay's work from 1934, are closely associated with Voronoi diagrams, named after Georgy Feodosevich Voronoi, his work from 1908, also called Thiessen polygons, named after Alfred Thiessen, his work is from 1911, which are formed by drawing boundaries between control points such that all hypothetical points within a polygon are closer to that polygon control point than to any other control point. So this is the basic idea. Delaunay triangles are created by connecting control points of neighboring Thiessen polygons. I will show you that later in an example. So once Delaunay triangles are formed, contour lines are created by interpolating along the edges of triangles in a fashion similar to manual interpolation. Delaunay triangles are desirable for this purpose because the longest side of any triangle is minimized, and thus the distance over which interpolation must take place is also minimized. And the shorter is, of course, better, because then the control points have a stronger influence on the values of these interpolated contour lines at the end. As strict linear interpolation along triangle edges leads to angular contour lines, smoothing of these lines is necessary to represent the underlying phenomenon properly. So the process applied here is the 3D equivalent of splining. So here you see hypothetical data showing manual contouring. So this is how it would be done manually. You have the control points, and then you connect those control points to form triangles. And along these lines, then, interpolation takes place, like manual interpolation, and you would get this result. Now, if we use the method, we can use these triangles and form these Thiessen polygons. Now, within these polygons, every point within this polygon is nearer to the control point that is inside it than to any other control point. So a point here is nearer to E than it is to D, for example. So this is the idea here. So, for example, this S point here, a hypothetical point S is closer to control point C here than to any other control point. So S is part of the Thiessen polygon associated with control point C. And then this simple linear interpolation along these triangle edges take place. And in the final step, these lines are smoothed. So it's a smooth interpolation along the Delaunay triangle edges. And this would be then the final result. The third method, automated inverse distance interpolation, also called gridding. Inverse distance interpolation involves 3 steps. First, laying a grid on top of the control points. So you lay a grid with regular cell sizes over the control points. The second is estimating values at each grid point or grid node as a function of distance to control points. So for each of the grid points, then you will have a value based on the control points nearby. And the third one is interpolating between the grid points to actually create a contour line. Because a grid is used, the inverse distance interpolation method is sometimes called gridding. The term inverse distance is used because control points are weighted as an inverse function of their distance from grid points. So that means control points near a grid point are weighted more than control points far away. So high distance means low weight, and therefore it's inverse distance. Although it is possible to use all control points to estimate each grid point, this is usually not done, as this approach seems unrealistic, because control points far away from a grid point are unlikely to be correlated with that grid point. Besides, computations should be minimized. So usually only those control points near to a grid point are really important for its value. Instead, various strategies for selecting an appropriate subset of control points were developed. For example, a defined number of control points falling within a quadrant sector of a circle with a defined radius to search the search radius. So this radius is called the search radius. I will show you that on the next slide. After grid point calculation, an interpolation between grid points is necessary to get the points for drawing the isolines. Angularity can again be avoided by smoothing the contours by splining. So this is the idea with this quadrant. It's one strategy to find an appropriate subset of control points. And here, the nearest two control points, the black dots, to a given grid point, here marked with the cross in the middle, in each of the 4 quadrants. So this is one criterion. So the large circle represents the search radius within which control points must be located. That means you have here, marked with the cross, you have a grid point. So you have a grid, a regular spaced grid. So there are more grid points. Maybe here is one, and so on. And around this grid point, there are the control points. You see the black ones, but also these white ones. And you define then with a circle a certain radius. So within a certain radius, and in each of the 4 quadrants, so you have 4 quadrants, you just use the nearest 2 of the control points. And these nearest 2 are now in black here. So there are more, but they are more far away, and you use only the 2 nearest in each of the quadrants. So this would be the criterion here. And then you interpolate them to get a value for this grid point. So again, the control points are those points where actually values are measured or data is collected. The grid points then, these are artificially introduced points to get a regular grid with values, but these values are interpolated from the control points. And the last method is automated interpolation by kriging. And this method is named after Dani Gerhardus Kriege, or Kriege. I'm not sure about this pronunciation. He is from South Africa, so the name might be Dutch, the original name, so it's maybe Kriege. But I guess in English, more or less now it's just called kriging. And so it's named after him. He developed the method in its, or at least the foundation of this method in his master thesis in 1951. And this thesis was about geological mining applications. So you know mining is important in South Africa, so it's an important topic there. And he developed here some mathematical foundations for this method. And usually the term kriging is written with a small k at the beginning. You will find it sometimes also with a capital K at the beginning. Kriging is similar to inverse distance interpolation in that a grid is overlaid on control points, and values are then estimated at each grid point as a function of distance to control points. So far, the method seems to be just the same. But, and then that's the difference, rather than simply considering distances to control points independently of one another, kriging utilizes the spatial autocorrelation in the data, both between the grid point and the surrounding control points, and among the control points themselves. To get a better understanding of how spatial autocorrelation is used in kriging, it would be necessary to understand semivariance and the semivariogram, but this is out of the scope of this introduction. There are two major forms of kriging. Ordinary kriging, the mean of the data is assumed to be constant throughout geographic space. That means there is no trend or drift in the data. Or second, universal kriging, trends or drifts in the data are taken into account. Kriging is more complex, but is often said to produce an optimal interpolation. But this is only true if it is applied properly, which is not always the case, in part also because some software provides simplified defaults which should be corrected to be appropriate for an individual application scenario. So you need to know your data, you need to know how this method works so that you can use it in the appropriate way, and only then the results will near to an optimal interpolation. Another advantage of kriging is that it provides a measure of the error associated with each estimate, known as the standard error of the estimate. This error measure can be used to establish a confidence interval for the true value at each grid location, assuming a normal distribution of errors. And this is, of course, a very good thing to assess, to judge the final result. So here, this example is taken from the English Wikipedia. It's an example of one-dimensional data interpolation, just to show you how kriging works. So here you have these confidence intervals. Squares in this diagram indicate the location of the data. The Kriging interpolation, shown in red, runs along the means of the normally distributed confidence intervals, shown in gray. So these gray areas, these are the confidence intervals, and it's assumed that they are normally distributed. And this red line is then the Kriging interpolation. The dashed curve shows a spline that is smooth but departs significantly from the expected intermediate values given by those means. So with splining used here, you see that especially here, you get quite a different result from the original Kriging result. Therefore, it should be done carefully, and sometimes it's better not to use that spline function, as it might introduce a greater error to your final result. Criteria for selecting an interpolation method. There are several criteria. A, correctness of estimated data at control points. That means, does the method honor the raw data? So that's one thing you should have in mind. Another thing is the correctness of estimated data at non-control points. How well does the method predict unknown points? Third, ability to handle discontinuities, for example, philologic faults. The fourth, the execution time. The fifth, time spent selecting interpolation parameters. And the sixth, ease of understanding the interpolation method. The correctness of estimated data at non-control points. So there were some studies about this problem, or this criterion. Isaacs and Srivastava evaluated triangulation, inverse distance, and Kriging interpolation, among others, for elevation data. And yes, I will continue here after the break. So we're talking about different criteria how to judge or how to evaluate which of the interpolation methods is the best. And one criterion is the correctness of estimated data at non-control points. So remember, there are control points. These are the points where actually data was measured or collected. But there are other points, like for example these grid points. These are non-control points. And the question here is, how correct are these values that are interpolated for these points? And one study that tried to evaluate triangulation, inverse distance weighting, and Kriging interpolation found the following. Overall, the study revealed that Kriging is best, although it was only slightly more effective than an inverse distance approach. They worked with elevation data. That's also important because the different kind of data might influence the result of such a study. Another study by de Klerk from 1996. This study evaluated triangulation, inverse distance, and Kriging interpolation for two types of data. Smooth data consisting of mean annual hours of sunshine, and abrupt data consisting of soil erodibility. So about the degree of soil erosion, the expected degree based on the steepness of the material, the rocks, and so on, the weather. Overall, his study revealed that there is little difference between inverse distance and Kriging methods, and that the number of control points used to make an estimate is more important than the general interpolation method. He recommended 4 to 8 for smooth data and 16 to 24 for more abrupt data. So that's interesting, that the number of control points is a more decisive question. And of course, if you have abrupt data, more abrupt data, you need more control points to find where such change in the data, an abrupt change in the data occurs. Now here is the state of South Carolina, US state of South Carolina. This is about rainfall data, precipitation data, based on heavy rains associated with Hurricane Hugo in 1989. And this is the result of triangulation. The contour lines represent inches of rainfall. Here is coastline. This area is the Atlantic Ocean coast. Now this is the result with inverse distance, taking into consideration all data for this interpolation. And this now is by using this quadrant method or approach. So not all data is used, only relevant control points near to the grid points. And B, this is now Kriging as the last method. And I go back here to see the differences here. It's quite interesting, of course, but it's hard to judge without the reference data. which is really the best method. So it would be necessary to have some reference data in a way that you have many more collecting points for the data, then you have more control points, and you can create a better result and compare it with the interpolation methods based on a fewer number of control points. There are limitations of automated interpolation approaches. Mulugeta compared automated and manual interpolation for two data sets: precipitation totals for a single storm event and bedrock surface altitudes. These data were automatically interpolated via Kriging and manually interpolated by experts. So these experts, they were climatologists and meteorologists for the precipitation data, and geomorphologists for the bedrock surface altitude data. A quantitative analysis revealed that the computer-interpolated precipitation map was significantly more correct than the manually interpolated one, and that there was no significant difference between computer and manually interpolated bedrock surface maps. Besides this quantitative comparison, comments from experts about the computer-interpolated precipitation map raised serious questions about the appropriateness of automated interpolation. Isolated peaks and depressions were overly smooth and too circular. The experts would have preferred elongated bands characteristic of storm precipitation surfaces. Features not warranted by the data points are portrayed, for example, a peak where a saddle is expected. And jagged lines and spurious details shown on the computer-interpolated precipitation map are artifacts and should be corrected manually. So, of course, if experts are doing this, they take into consideration a lot of additional information. So they have a lot of knowledge about such a storm event, for example. And therefore, of course, if you compare their result with an automatic method, and this automatic method, at the moment at least, cannot take into consideration this expert knowledge, then it is to be expected that there are some flaws or some drawbacks. Let's take a look at these results of this study. So we have here the computer-interpolated versus the manually interpolated precipitation maps. And so it's about the precipitation topic. And the first map here is a computer-interpolated contour map. And the value interval here is a ½ inch for each line. And A1, A2, A3, A4, and A5, these are isolated peaks and depressions, and they are overly smooth and too circular. So they're near to a circle, which is not to be expected for this kind of precipitation data in this kind of storm event. B4, that one here, this peak is not warranted by the data points. So based on the data points, we cannot have a peak here. And D1 to D4, so this is along the lines here, D1, D2, D3, D4, and down here you have also here F1, F2, F3, F4. These are jagged lines and spurious details, and they all are artifacts. So they are artificially created by the automated interpolation method. So with the jagged lines, it's meant that these smaller changes in the curvature, these are the jagged lines, and these small changes are not within the data. So you cannot get such a line based on the control points available in this situation. And this now is a manual interpolated contour map. And this is another manual interpolated contour map, so by two different experts. Which is also interesting that the experts, they do not agree on all the details. For example, here, the 1-inch line, and I go back here, they are not connected. So that's an open question. Obviously, there are not enough control points to clearly say that. But the automatic solution did not connect the two. But you see that these details and these errors that are part of this automated version are not here in the two manual versions. But also here are differences between these two manual solutions. So of course, you get a better solution if you have more control points. That's the most important point or thing to take with you. It's not always possible. So for some kind of data, we have only a limited number of control points, and therefore we have to use one or another kind of these interpolation methods. I guess in the future, more expert knowledge will be used also within these interpolation methods. That means we will have interpolation methods for certain kind of data, and not only general methods that are used for all data, no matter what the characteristics of these data are. Another approach is Waldo Tobler's pycnophylactic approach. Although the automated interpolation methods described so far were developed to handle true point data, they also have been commonly used for conceptual point data, and thus for isoplace mapping. This is possible by assigning values of enumeration units to their respective centroids, which then serve as control points for interpolation. So these centroids, these are just points in the center of each of the enumeration units. And they are then used as conceptual points. Waldo Tobler's pycnophylactic or volume preserving. So this is just a technical term for volume preserving approach. Is a more sophisticated method to handling conceptual point data. A simplified algorithm developed by Nina Lam, 1983, illustrates the pycnophylactic character of Tobler's method, but not the smoothness constraints that he specified. So I will show you a simplified example after the next two slides. So it's a bit simplified algorithm compared to the original one developed by Tobler. To understand the idea behind this method, consider the following. First, the standardized data associated with enumeration units is represented as a clay model, in which each enumeration unit is raised to a height proportional to the data. Then second, the objective of the pycnophyletic method is then to sculpt this surface until it is perfectly smooth, but without allowing any clay to move from one enumeration unit to another, and without removing or adding any clay. Relating this concept to the other introduced interpolation approaches, volume preservation can be seen as a form of honoring the data associated with each enumeration unit, because the volume for each of the enumeration units stays the same, it's constant, so there is no change within, or not within, but for the whole enumeration unit there is no change. Within the enumeration unit there is change. It's necessary to smooth the data values between the enumeration units. You will see that in the examples. But the method should only be used with quasi-continuous phenomena. So it's quasi means nearly as continuous phenomena are treated. So this here is the basic idea. You have, for example, here 5 enumeration units in different colors here. And then to smooth, so this in this interpolation, the smoothing takes place within each enumeration unit. So the lower ones, they have to, as you see here, 5, 10 iterations, 15, 20, 25, and so on. So the surface is smooth more and more. And you see how this is done here. So the amount of clay, as in this metaphor, is the same. So that means if you lower here some parts, that means you raise other parts at the same time, so that the volume stays the same. So you see here, some parts are raised and other parts are lowered. And this happens here for all the 5 enumeration units. And at the end, you have this smooth interpolated volume. And with numbers, so this is just to explain the basic steps of this pycnophyletic or volume preserving contouring based on Lam's algorithm. So this is the more simplified algorithm. And it's a very simplified example, of course. You have just 3 hypothetical enumeration units, E1, E2, and E3. They have different areas. So the first one here is smaller. The other 2 have the same size. And then you have some data for these units. So the raw data here is 25, 30, and 42. And then you put an overlay on these enumeration units, square cells, like here. And then in C here, you compute these cell numbers by dividing the raw count for each enumeration unit by the number of cells in that unit. So it's simply here for E2, for example, you have the number 30, and you divide 30 by 6. This is the area. You have also 6 squares here. They look a bit more like rectangles, but doesn't matter. These are the grid cells, and for each of the grid cells here, you compute 5. And for these 6, 7, because it's 42. And for these 4, 6.25, because it's 26. And then you smooth the cell values. This is achieved by averaging neighboring cells. So here you build an average between the values for the cells. And then in E, these smooth values are adjusted so that the sum within an enumeration unit equals the original total sum for that enumeration unit. And that means the volume is preserved. So this is where the name pycnophylactic comes from, volume preserving. So if you now add these 4 numbers, you get the original number for this enumeration unit. So this describes it step by step, this method. And applied here to data of wheat harvested in Kansas, 1993. So this is the pycnophylactic approach, which expressly deals with the fact that the data were collected from enumeration units. But one problem that you see here, you get very high numbers here in this area. So if you compare this with the Kriging method, so this approach treats the aerial data as conceptual point locations. And you see, especially here, it's quite a difference. So you have here 50, and then go back here, you reach 70. And also here, the rest of the map, it looks better, which does not mean that it's nearer to the original data. So here you have wheat harvested, and it's about the percentage of land area for each of the counties. And the pycnophylactic method now deals each of the enumeration units like a cell, if you like. And while here, this is done with conceptual point locations. That means for each of the counties, you have one point in the center, and for this point, you use the harvested wheat. So the percentage of the land area that's used to harvest wheat. So you get, of course, then different results here. Now, the last part of this method here is arithmetic mapping. It's about symbolization. Typically, we use contour lines to depict smooth, continuous phenomena. They are easy to produce, but relatively hard to interpret for untrained people. Usually for us, it's not a big deal, but for untrained people, it might be difficult to interpret contour lines. Often also hypsometric tints or shaded areas between the contour lines are used, with or without drawing those contour lines. This enhances the ability to visualize a three-dimensional surface because light and dark tints or various color schemes can be associated with low and high values, but the limited number of tones suggests a stepped surface. And this is not really what we want, because we are dealing with continuous phenomena usually, so the surface should not look like being stepped. That's one reason why also continuous tone maps were developed, again also with or without contour lines. This symbolization gives a much better impression of the continuous character of the depicted phenomenon. But it is difficult to associate values with certain locations. So that's the drawback here. Contour lines, hypsometric tints, and continuous tone maps can be combined with hill shading. So hill shading is often also used. Another form is a fishnet symbolization. This assists in interpreting smooth, continuous phenomena. Same disadvantages as the prism map, including the blockage of low points by higher ones and the fact that rotation might produce a few unfamiliar to readers who normally see maps with north at the top. So we see an example then. Also 3D techniques like stereoscopic views, stereo pairs, for example, or anaglyphs are possible symbolization solutions. So here you see now several examples with different methods for symbolization. Here using only contour lines. The next one is combining contour lines with hypsometric tints. This one is the fishnet symbolization, but usually you have to turn it or rotate it in a way that the high values are more in the back and not in the front. Otherwise, the higher areas cover the lower ones. And this rotation then, of course, leads to an unfamiliar view. This is again South Carolina, and people expect it, to be in this position, the gray one here, but that one is turned. And because the high values, remember, the high values for the precipitation are near the coast. So here near the coastline are the highest values. And this makes it a bit more difficult to understand this method. But depends also on the data, of course, because for some data, there might be here the lower values and here the higher values, and then you can easily present it in the familiar way. The fourth example here now is a continuous tone visualization. So this is analogous to those used on unclassed choropleth maps. So we had an example there when I talked about classed or unclassed maps. And it's also possible then to combine continuous tones with contour lines, which is, I think, quite a good solution. As on the one hand, you see that this is a continuous phenomenon. On the other hand, you have the lines with the values so that you easily can also read the values, the data values from the map. And here also several methods are compared. So here we have a color gradient with a data grid superimposed to get a 3D surface. Here this is combined with contour lines. And here you see difference between color gradient and a contour line with hypsometric tints. Of course, you have the advantage here that you clearly know about the values, the range of values. Here, this is more fuzzy, more complicated to see certain numbers, to read or to analyze the map based on certain numbers. But this gives you the impression that this is a continuous surface, while here, maybe for untrained map users, they think of a stepped surface. And at the end, one application. This is about the average annual precipitation in the state of Washington in the United States from 1981 to 2010. And you have annual precipitation in inches here. And here we have continuous tones combined with contour lines. And yeah, this works quite good. I would add some numbers in the map. So to annotate the lines so that you immediately know, okay, this is the line for this amount of rain, because here it's quite difficult then to find exactly the numbers here. But you get a very good impression of this data in this US state. So that's the end of the isorhythmic map. And I want to continue with part number 5. And the next topic is interaction. I use here mainly a PhD thesis written by Robert Emmett Roth. You remember maybe that I used also his contribution about the visual variables. This was also developed by Robert Roth. And interaction is, of course, an important topic. And it was really necessary that someone starts dealing with this topic in detail. And Robert Roth did that. And you see here in these two diagrams, the one on the left side, you know already. I talked about that. It's from McAtran, this radial category of maps, or the map as a typist. And now Robert Roth, he's writing here, or he's naming this digital map. But of course, everything that's here in that diagram on the left-hand side is also true for the digital map on the right-hand side. But with the digital map, also interactivity and the option to disseminate maps via the World Wide Web, these now are very powerful and interesting new options for maps. And therefore, he named this digital map. So we again have two axes here. The one is about, the horizontal one is about web dissemination or not, non-web dissemination, or the vertical axis here is about the interactivity. So no cartographic interactivity or high cartographic interactivity. And he also uses now this new radial category digital map here to name different products, different kinds of digital maps, and place them according to their functionality, their kind of dissemination, their degree of interactivity within this diagram. And if you wonder what YAH means, these are you are here maps. So these are this kind of maps you often find on hiking, along hiking trails, for example, or also in shopping centers or at airports. These maps want to help you to locate yourself so that you know where you are right now. And usually you find this name there, you are here maps. So there's a red dot maybe saying you are here on the map. So all of you know this kind of maps, but maybe you're not familiar with this kind of abbreviation. And yeah, it's interesting, and it sees also how powerful, of course, these new categories are to change the way how we deal with maps, how we can use them. And this chapter now is about this aspect of interactivity. So it presents some of the basic theory about interactivity. We can discriminate three components of cartographic interaction: humans, computing device, and the map itself. And therefore we can see the cartographic interaction problem as user-centered, technology-centered, or interface-centered. We can say cartographic interaction is defined as the dialogue between a human and a map mediated through a computing device. This gives rise to three areas of emphasis within a science of cartographic interaction. And these are these three areas of emphasis. Digital, so usually it's digital cartographic interaction. So this is the dialogue between a human and a map mediated through a computing device. But we can say that a kind of limited interaction was and still is also possible with traditional paper maps. Just think, for example, about adjusting map extent by folding the map, or symbol sizes by changing the reading distance, or highlighting text or symbols with marks or pins on the map, on the paper. So these are all, in fact, different kinds of interaction. But of course, with digital maps, we have many, many more options and possibilities. It is necessary to distinguish cartographic interaction from cartographic interfaces, the digital tools through which the cartographic interaction occurs. For cartographic interfaces, the distinction between interface style and interface design is also an important one. Interface style describes the way in which user input is submitted to the software to perform the cartographic interaction. Interface style includes direct manipulation, pointing at the map or custom interface widget to manipulate it. Menu selection, selecting items from a list. Form fill-in, keying in text to indicate parameters of a desired action. Or common language, using simplified syntax to indicate a series of desired actions. Or, and this becomes more popular nowadays, also natural language, using spoken language to submit a question or command. Interface design describes graphics, sounds, haptics, etc. that constitute the interface widget and its feedback mechanism, producing its look and feel. Success of cartographic interfaces is evaluated in terms of their utility and usability. Interface utility means the usefulness for completing the user's desired set of tasks, while interface usability is about the ease of using the system to complete the desired set of tasks. So these are two different but related things. Cartographic interactions and cartographic interfaces are inseparable. That means digital cartographic interaction cannot occur without a cartographic interface, and its utility and usability is determined by the kind and quality of cartographic interactions provided through it. This diagram shows the relation between interface complexity and user motivation. So here we have user motivation, and here we have the interface complexity. And the success cartographic interaction is contingent upon the relationship between these two. That means if a user is highly motivated, but the interface complexity is low, then it's a failure. And also the other way round is true. So if you have a high interface complexity, but a low user motivation, then it's also a failure. Therefore, these two, they have to work to fit together. So if you have a higher complexity, you need also a user with a higher motivation. Then at the end, you will have success. In general, the cartographic interface enables cartographic interaction by providing affordances and feedback. So these are two important terms, affordances and feedback. Affordances signals to the user about how to interact with the interface, while feedback signals to the user about what happened as a result of the interaction. The fundamental types of cartographic interactions that altogether constitute an interaction session are called interaction primitives. A useful framework for identifying interaction primitives is the Stages of Action model developed by Norman, 1988. It describes an individual exchange in the overall interaction conversation in a sequence of 7 observable steps or stages of interaction. I want to show you an example for affordances. So when you compare these two doors, then you see immediately when you approach them, you get information how to use them. You quite probably you will try to pull this door and you will try to push this door. But with that one, this is not so clear, and therefore you have an additional information. So we can say these two affordances are successful, this one is not, because we don't know, and we see that we should push, and therefore it's necessary to write that there. So you see the difference between well-working and not well-working affordances. And before I continue then with the stages of action model, we have our second break now. So, welcome back to interactivity. The 7 stages model and the 3 O's of cartographic interaction. So Norman developed this model, and this model here describes 7 stages of a single execution evaluation loop, while a taxonomy of interaction primitives could be offered at all of these stages. There are 3 common approaches: an object-based, an operator-based, and an operand-based. They are highlighted here. But first, let's go through these 7 stages. So we have the user here, we have the computing device, and we have the map, these 3 parts. And at the beginning is forming the goal, then forming the intention, specifying an action, executing the action. Then here is the operand, and the 5th, here is the first 4 I just mentioned. These are about the execution. And the other 3 here, the 5th, 6th, and 7th, are about evaluation. So it's about the feedback, perceiving the state of the system, interpreting the state of the system, evaluating the outcome. And then usually we decide what to do next. That means we are forming the next goal and the next loop starts. The 7 steps in the stages of action model are also described here on the slides. So the first one, forming the goal, is what the user is trying to achieve in general. As an example, exploration or presentation. The second step, forming the intention or objective, the task the user wishes to complete. For example, reclassification of data. The third one, specifying an action, the translation from the user's objective to the functions provided by the cartographic interface that are perceived by the user to support this objective. For example, based on implemented affordances, an operator for data reclassification is identified. The 4th step, executing the action, the doing component. That means the physical human input. For example, the identified operator for data reclassification is executed. For example, pressing a button, typing in something, saying something, and so on. And then the evaluation part starts with the 5th stage, perceiving the state of the system. Following the execution, feedback is provided to the user indicating that there is a result of the action. For example, the new classification is displayed. I'm sure we all made this bad experience that we are doing something, we're pressing a button and nothing happens. So we don't know what's going on. Maybe the computer is doing some computation, so needs some time, or it doesn't work, the function is not available, or there's a problem with the program, and so on. So if there is no feedback, we are getting confused. And therefore, feedback is very important. Next stage is interpreting the state of the system. The result of the action is interpreted. That means the user tries to make sense of the update. For example, the new classification is analyzed. And the last stage, evaluating the outcome. The result is compared with the expected or desired result. That means conducting a validity check and a comparison between outcome and initial goal. For example, is the new classification correct? Is the classification better now? These are typical questions in this example's context. The 7 steps in the stages of action model. Related to them are 2 general kinds of potential failures in communication between users and an interface during an individual interaction exchange. The first is called the gulf of execution. The user is uncertain what to do with the cartographic interface, or certain of what to do with it, but uncertain of how to do it. So this refers to interruptions in the first 4 steps on the left-hand side of the loop. To avoid problems, it is necessary to understand users' needs and intentions and to implement strong affordances. And the second is the gulf of evaluation. So this is then on the right-hand side. The user is uncertain what she or he did with the cartographic interface, or uncertain of what the resulting change means. This refers to interruptions in the final 3 steps. To avoid problems, it is necessary to provide prompt and informative feedback. Therefore, these 2 terms I mentioned are important ones: affordances and feedback. Related to the stages of action model are the 3 O's of cartographic interaction. The first O is related to the objective-based approach, linked to the second stage, forming the intention. Interaction primitives as kinds of tasks the user may wish to complete with the cartographic interface. The second O belongs to the operator-based approach, linked to the third stage, specifying an action. Interaction primitives as kinds of operators the user can perceive based on implemented affordances. And the third O relates to the operand-based approach, linked to the operand, the digital object with which the user is interacting, between the 4th stage, executing the action, and the 5th stage, perceiving the state of the system. Interaction primitives as kinds of operands based on their possible properties. So these are the most common 3 used to classify also the different interactivity options, let's say. Now the first here, these are examples from different works, so from different publications. You see the authors here, always with the year, the name and the year of publication. This is about the objective-based primitives, so the first of the 3. And this is a concept map. So Robert Roth, he analyzed the literature and tried to develop such a concept map with the relevant terms related to the objective-based primitives. The concept map shows the relationships among extant objective-based taxonomies and the relative frequency of the included interaction primitives. So the frequency is, of course, shown by the size of the terms. So larger ones are used more frequent in the literature. The map can be segmented into 3 subsections So you have these gray dashed lines, and they discriminate here between three subsections. Top, a concentrated set of simple taxonomies that include the primitives identify and compare. So these are relatively simple ones, and very often used are these two terms, identify and compare. In the middle, this section here, two taxonomies that expand upon the compare primitive. So two means two publication, and they expand, so they have additional ideas, additional primitives for the objective-based part of the interaction circle. And then there is an outer rim, unprecedented or orthogonal taxonomies that have minimal overlap with others. So he found other ideas as well that are less important, let's say, but he tried to collect all this information here to give an overview, and I decided to include it here also in the materials to give you a better idea what is meant here with objective-based primitives, and how these terms are related to the different stages within this 7-stage model of interaction. The second is a concept map of the operator-based primitives. And some of these terms might be more familiar to you, like zooming, for example, or also panning, recentering of a map, let's say, or any other kind of visualization. And now we have, of course, many of those publications now are different ones, not the same as before. Some are dealing with several of these types of primitives at the same time, but others are concentrating on just one. So it's different. And you see here, there is an inner circle here. So there are these two segments. In the center, commonly included primitives with contradicting or inappropriate definitions. So what does that mean? They're also larger, you see, they are used more often, brushing, focusing, linking. You find them in the respective publications, but they are often used in different ways. So they are not defined always in the same way. They are often defined in different ways. So in one publication, for them, brushing means this, and in another publication, brushing means something else. So this is the problem here. Therefore, contradicting or inappropriate definitions, this is meant here. And the outer rim, so most of the terms are outside of this circle. These primitives included in only one or two taxonomies, but that altogether exhibit several common themes. So they are not, let's say, they're not commonly used. They're used only by one or two publications usually, and therefore we don't know at the moment which of them will be used more frequently in the future, and which are not. But at least you see different options how to describe operator-based primitives. And the last one then is about the operand-based primitives. And here you have two segments. Top, it's type-centric taxonomies, discriminate primitives according to characteristics of the represented information. And bottom, state-centric taxonomies emphasize the linear workflow from raw data through on-screen rendering a sequence of computational transformations. So this is more abstract, and these 3 slides are more background information, let's say, for those who are more interested in this topic. The next slide sums up the most relevant terms, so that's easier to understand and follow. So we have here now an empirically derived taxonomy of cartographic interaction primitives. And here it's about the goals, here about objectives, here about the operators, and here about the operands. And the goals, you know these 4. We talked about them in DiBiase's model at the beginning. It's the theoretical foundations, models that are relevant for visualizations. So we have the 4 stages: exploration, analysis, synthesis, and presentation. Another way is about the desired outcome of interaction: procure, predict, or prescribe. Objectives with increase in sophistication: identify, compare, rank, associate, delineate. So these are typical objectives. When we start interacting with something, we want to identify a certain location, a certain object on the map, for example. We want to compare different areas, and so on. Then operators. There are work operators and enabling operators. And the work operators, some of them are well known. I mentioned zoom or pan, but also to filter, to search, retrieve, calculate, reproject, overlay, resymbolize, sequence, arrange, re-express. So these are all potential operators we can use then to interact with the visualization or the map. Enabling operators are import, export, save, edit, annotate. So they have a bit different kind of function, more general. And the last one are about the operands. So search target and search level. Search target is, for example, space alone, attributes in space and space in time. And the search level, general or elementary. And on the next 2 slides, these objectives are compared, or not compared, they are related, combined with the search targets. And to show you different kinds of examples here. So we have definitions and examples of each objective and operand primitive combination. So objective is here identify, compare, rank, and on the next slide then also associate and delineate. And operand primitives here is about space alone, attributes in space and space in time. And for all of these combinations now we have examples here. I will not read that. You can do that by yourself. So you get a better impression what is meant here. I want to go on with the next section. The next topic is web mapping. In part, it's related to interactivity because web maps, of course, they are often also interactive. Technically speaking, the World Wide Web and the Internet are not synonyms. They are fundamentally different. So sometimes in everyday speaking, we speak of the World Wide Web and the Internet, and we mean more or less the same thing. But technically speaking, that's not correct. The Internet is a series of interconnected networks whose purpose is to transfer files. The TCP/IP, the Transmission Control Protocol Internet Protocol, which was introduced on 1st January 1983, offered the ability of a globally based network. And some say this is the birth of the Internet, 1st January 1983. The World Wide Web, short, often just called the web, was developed a bit later in 1989 at the Conseil Européen pour la Recherche Nucléaire, CERN, near Geneva in Switzerland. The web is a series of interconnected hypertext documents that are shared over the internet between a computer user and a remote computer. So the web uses the internet. It is one application, let's say, of the internet. These documents are viewable through a web browser. In short, the web makes it possible for a computer user, the client, to specify a URL, a uniform resource locator, through a web browser interface. The URL is changed into an Internet Protocol IP address. Then this IP address is used to access the remote computer, the server, on the Internet network. And then the server delivers the requested information through HTTP, Hypertext Transfer Protocol, back to the web browser on the client's computer. The web browser finally takes the hypertext markup language, HTML, and configures it so that the client's computer can display it on screen. So this, in short, describes the process and how the web is related to the internet. I guess most of you know about that, but maybe it's also a bit new to read that in English. A classification of websites which incorporate cartography based on 5 continua. First, pre-existing maps versus custom-tailored maps. Some websites provide maps that are already made. Other websites offer users the ability to create their own custom-tailored map, for example, through a real-time map browser or a map generator. The second is about interaction, low interaction versus high interaction. Cartographic websites offer different interactivity levels, from none, so that's just a static map where you cannot change anything, you cannot interact with, to GIS-like functionality. That means you have even the option to do some analysis, for example. Sorry. The third is about distributed data versus user-contributed data. Some websites provide spatial database catalogs or libraries and also downloadable data. Other websites offer individuals the opportunity to contribute their own data for others to download. This includes the idea of prosumers. That means users of such sites are producers and consumers at the same time. It also has to do with VGI, volunteered geographic information, citizen science, and so on. So there are several interesting topics around here. Another possible distinction for classification is updated data versus non-updated data. This reflects the timeliness of the data available to the user. And the fifth one is about animated maps versus static maps. Some websites provide maps with temporal or non-temporal animations. Other websites just offer static maps. These continua are not an exhaustive way of describing every cartographic website. Certainly other continua are possible as well. So continua means that between these two extremes or endpoints, you have, of course, several variations. Sometimes you have a static map. Yeah, here the example is not so good, because if any part of a static map is animated, then it's usually treated as an animated map. But with other of these five distinctions, it is possible to think of different in-between states and not just the two extremes, and therefore it's treated as a kind of continua. The maps on the next slides exemplify the 10 ends of the 5 introduced continua. So I will show you some examples on the next slides. The first continuum, pre-existing maps versus custom-tailored maps. And this is the example for pre-existing maps, therefore it's underlined. So this is a map of a national park in the United States about the Lassen Volcanic National Park in California. And this is a map that maybe has been adapted a bit, but it existed before the map was used, or before it was used for the map. It's also printed on paper, and therefore it's a pre-existing map. Here you see a section of it enlarged. Or the other end of this first continuum is custom-tailored maps. And here you have a map of healthcare assistance receipts by county for the United States for 2002, created through American Fact Finder, a custom-tailored mapping site. Their users have a wide range of options to influence what is visualized and how it is visualized. So interactively, you can produce a map, and therefore you get a custom-tailored map at the end. The second continuum here is about low interaction versus high interaction. In this case, we have low interaction, so low is in fact the state in between them. So it's more between no interaction and high interaction. And this is the first Chinese city map of Copenhagen in Denmark. And here you see a section of it. It's a pictorial tourist map, quite nice. And of course, this would also fit in other categories like static maps, for example. But this has been produced for the web. So it's therefore a good example here. The second continuum here is low interaction now. Unfortunately, this is offline at the moment, to my knowledge. There is this color brewer I mentioned already, and this one is a similar idea, but it's about type. So what kind of letters, what kind of fonts are used in maps, and it's called also type brewer, referring to this color brewer. And it's a website, or was a website, that offered a low level of interactivity. So it offered a quick and easy way to explore typographic alternatives and see the impact that various elements of type have on the overall look and feel of a map, which is a very interesting idea. But yeah, I could not find it again, unfortunately. But you see some screenshots here about this application online. So you're part of Italy with different kind of fonts, and how this changes the impression. And then here is a medium interaction, a screenshot of the National Atlas of the United States showing major hurricane paths in the Western Atlantic Ocean during the 2000s. This site allows to select a topic, to zoom in and out, and to identify various data attributes. And yeah, here it is defined as medium interaction based on that. Or then on the high interaction end of the second continuum, this is one of the Earth view maps as an example for Earth viewers in general. These sites typically offer a wide range of interactively controlled functions. So of course there's also Google Earth, there's Whirlwind from the NASA. The third continuum is about distributed data versus user-contributed data. And this one is for distributed data. The USGS, the United States Geological Survey, has promoted the national map as a one-stop shop for geospatial data. The eventual goal is to make it a nationwide warehouse of geospatial data that is accessible to the widest community of geospatial data users. And you can find a lot of different data there, and yeah, everyone can use that for free. The US, they have a policy that the taxpayers already paid for this, because the taxpayers finance the authorities, here the USGS, to collect this data, and therefore they don't, or there's no need from their point of perspective, it's no need to pay again then for the data, and therefore it's available, most of it. And there are interesting examples for user-contributed data. This one here is the New York City subway smell map. It presents the subway routes, station stops, and associated smells throughout the subway system in Lower Manhattan. The website relies entirely upon users to supply the data. The last time I checked that link, it was unfortunately broken, so I don't know if it still exists. But you see here how this worked. So there were symbols. You can click on stations, and then the symbols are displayed here. And here you can read by yourself what kind of smells to expect at each of these stations. Another example for user-contributed data, the eBird website is an example for citizen science. Citizen science is scientific research conducted in whole or in part by amateur or non-professional scientists. The eBird website documents bird observations. So there are quite many people out there who are interested in birds, and with such websites, data can be collected with their help. You have a kind of a form. Where did you birds? You type in the location, the characteristic of the location, or exact coordinates, and so on. And then, of course, you can upload a photograph, or if you know about the bird's name, you can write that down. And finally, there you have such a map here. And this is about how many birds are observed in certain areas. Of course, this depends highly on how many people getting involved. In some areas, not many people are involved. In other areas, many people are involved, and therefore there are more observations. This data is relatively uncertain, and the resolution is therefore also coarse. So it doesn't make sense to have a very high detailed resolution here. Therefore, they decided to have only this coarse blocks, a low resolution map, because this better reflects the low resolution of the data. And another example is the roadkill. It's also an example for citizen science. This project aims at investigating which species and how many animals are killed on roads. So it's kind of, at the first moment, You might think that's strange idea, but for researchers, it's a very interesting data because it's like it also has to do with observations of animals and also where cross animals, streets, and so on. What kind of animals? You can collect here a lot of information that only with citizen science is possible because it's impossible to have so many researchers or people who help them to cover whole countries or many roads within a country. And it's, as you see here, it has been developed in my home country, in Austria. AT stands for Austria. And yeah, just a few images of this website. So here you see then the locations. You see here this is about frogs, kind of frogs. This here is a city in England, Derby. And you can log in then, and you can also upload then the information, share it with others. So here, this image of a frog is generally used. Not all the animals are frogs. So here's a fox, for example, and others. It's also possible to upload an image, but of course, this is not really nice looking. So that's not a really good idea for everyone to see that, but it's interesting to collect the information. And there's even a ranking. So how many of such locations have been uploaded by whom? And you can zoom in and out, get maps of different countries, different locations. And yeah, these are different forms to fill about the information they collect. And the fourth continuum is about updated data and non-updated data. Typical examples for updated data are this flight radar or FlightWare pages. I guess you have checked them out before. It's also interesting to take a look now because there are not so many aeroplanes out there at the moment. And these are examples for real-time or near to real-time websites with so-called live maps that are updated at least in very short intervals. So yeah, I guess you know about these sites. It's even possible to click on the planes and get information about them. So what kind of aeroplane is it? From where does it come? To which airport does it fly? And so on. And here this other one, FlightWare. And non-updated data, of course, there are libraries scanning maps. So these are usually then static maps. And I tried to find an interesting example of Wuhan. So this is from the Perry Castaneda map library at the University of Texas at Austin, USA. And you find a lot of maps there. And the one I've chosen here is from the US Army Map Service from 1945, so relative old map of Hanko. And within this map, you see it here in the back, here is the section of our university. So here is Luochashan. And yeah, you can check it out later if you're interested. It's also possible to download it, so you get a relatively high resolution, as you see here, so you can see all the details on that map. And now the last examples here is about the distinction between animated versus static maps. The first is an animated map that shows the number of US and other coalition fatalities in Iraq, so Iraq war. Coalition fatalities, and you can check it out at that site. I hope it's still available. I've just saved some screenshots that I will show you. And yeah, you see where there were fatalities, and if there are more fatalities, then the color is larger or darker red. You can read the details here. I want to go through it a bit more quickly because I want to finish this section today. So you start with the red button on March 20, 2003. And then you see first the outline of Iraq. And then it starts here. These are screenshots now from this animation. And you see you can select the countries, from which countries are fatalities. And you can decide if you want to see also place names. Here there are no place names. And you see here the date changes, so it's then later. And where do people die from which nation? It's also possible to check that out about the different nations here. And of course, it's more interesting to see it as an animation. This is just to give you an idea how this looks like. And the last examples are about static maps presented online. Of course, you find such examples also in map collections. The David Ramsey map collection is a very big one, for example, where you can also check out maps related to China. This one here I liked because it's an older one, and they're also beautifully made. It's from 1930, and it's a map of a part here of Hubei province around the Zhangjiang. And yeah, I show you these examples at the end today. So you have here Hankou, Hanyang, and Wuchang. And yeah, here you have Yang. And here I have enlarged this section of Wuhan. So it's quite interesting to see that. Also the script is quite interesting because it's westernized. Even the Chinese characters are westernized in their style. And yeah, it's from 1930, so it's quite old in the meanwhile. A very nice example. So you find a lot of things online, of course. And this is the last example for today. I want to thank you for your interest, and hope that we meet again next week, again in good health. So stay healthy if possible, and have a nice rest of the week. Thank you for your attention and interest. Have a nice day. Bye-bye.